Hi, today we're going to take a look at the calculator applications with the derivative. So we're going to use the TI Nspire, wonderful little calculator. So TI, if you're listening to this, there's a good plug. I would expect at least 10% of all calculator sales based on this video. Alright, so many people know that Alan Shepard was the first American in space, but many people don't know he was the first human to play golf on the moon. In 1971, he hit a golf ball on the moon, and the equation for the height of that ball is modeled by this equation. Just to let you know, I did make up this equation. So before we do anything, we are going to type the equation. Now, he claims to hit the ball over 200 yards, but we'll see. So first thing we're going to do, of course, is we're going to graph the equation. I'm going to go to my little equation editor here, and I'm going to type that in. And it's negative 1.635. We don't use t, we're going to use x squared plus 100x. Now if I were to graph this, oh no, I can't really see anything, so we have to change the window. Now, many different ways you can change the window. I don't want the label, so I'm going to go kind of use a little bit of common sense here. So I'm going to go menu, I'm going to go window, and I'm going to edit the window settings. I don't like zoom fit necessarily. Now the x-axis is time. I'm going to say the ball is going to be in the air for quite some time. So let's go crazy. Let's go 60 seconds. A minute, full minute in the air. My y-min, it's going to go up pretty high, so I'm going to make that like negative 100, just so I can see things. And my y-max, I don't know how high it'll go, so I'll go 1,000, just to see. I just want to see if I can see the graph. And if I look there, oh no, obviously I didn't make my dimensions big enough. So I'm going to change my window again. Window settings, obviously my time wasn't enough, but I don't need to go too much further. Let's make that 80. And my height almost looks good enough, so I'll make that 2,000 instead. And oh look, now you can see the full graph. This is what you want to see, the height of the ball. Now, let's go ahead and use this to answer some questions. So the first thing we're going to do is find the height h of 3. So, and explain what it means. Well, h of 3, that's just finding the value on the calculator. So to get the value on the calculator, on the Nspire, you're going to go to menu, and from menu, you're going to trace. And then you're going to hit what's called graph trace. So I go to menu, I go to trace, and I just go graph trace. I press on 1, and I just type in the number 3. Type in 3, it shows up here on this little bitty this box right there. I press enter, and it gives me the height. And I get h of 3 equals 285.285. How cool is that? Now the units, we are in meters, so this is going to be meters. So the question is, what does this mean for us in terms of the calculus? We're going to write this out. And it says, at 3 seconds, the ball is 285 meters above the moon. And there's our answer there. Now I'm going to switch to a black pen here, make sure it looks a little bit higher. Now that one I think most of us already knew how to do. But today we're going to take a look at this h prime of 3. And you may recall, this is what we call the derivative. And it finds the slope for us. It's a rate of change right here. So to find this on the calculator, again, we are going to go to menu. This time you're going to go to, so when you type in menu, press the menu button, you're going to analyze the graph. Analyze the graph, that's number 6. And then if you look down here, in pre-cal you use 0, minimum, maximum, intersections, but now we have this new one, dy dx. And we've already learned that this is one of the ways that we show derivative. So I'm just going to type in the number 5. And it's going to ask me for what position I want to find. So we're looking at this dy dx. And to get the answer, h prime of 3, just like with the value, we're just going to type in the number 3 and press enter. And it gives me this 90.19. Now that is an instantaneous slope. That's why it shows up at a point. At this point, that's the slope of the line. And in units, because it's a rate of change, it's the slope. Remember, my x-axis is time, my y-axis is meters, so it's meters per second. And to explain this, we would say the ball is increased, the ball's height, be specific, sorry, is increasing at a rate of 90.19 meters per second. And there we have it. Very easy to do. Calculators, these are your friends. Okay, now for part C, it says, what is the speed of the ball when it hit the ground? So we have to think, oh, when does the ball hit the ground first? So we have to say, okay, that is where, when it hits the ground, we know that the height has to be 0. So again, we're going to use a calculator. You go to Menu, you're going to go to Analyze the graph, just like we've been doing, Menu, Analyze the graph, and we're looking for the 0. Where does the ball hit the ground? This is called a 0. So I type in 1, and if you notice, it asks me for lower bound. Now there are two places the ball hits the ground. Way down here at the beginning, and way over here at the very end. Remember, this function models the height of the ball. So when it's on the x-axis, it's on the ground. Now we don't really care about this one. That's when he hits the ball. We only care really about this spot. So to find that, we're going to go lower bound. I'm just going to click to the right of it, left of it somewhere, and I'm going to scroll. Now look, if I scroll, if you notice, it gives me this little shady region right here. If I scroll over to the right, it gives me this value, and it's kind of hard to see because it's kind of, the answer is kind of right in where the upper bound is. Sometimes it'll show it, but in this case, I'm going to have to hit enter, and it gives me this 61.16. So the time is 61.16, and that's going to be seconds. But we're not done. We want the speed. So speed is a rate of change, which we call the rate of change, which for us means derivative. So we want to find the derivative of the height at 61.16. And we've already done that before, so we know how to do that. Menu, escape, menu, there we go. Get back into the screen sometimes. Oh no, smudge. Analyze graph, looking for the derivative, 5. I hit, and I just type in 61.16. Now it's kind of hard to read, but there's all these little things right here. But if I read that, this is like negative 99.99, which is like negative 100, and that's going to be meters per second again. So this is saying, be very careful, the ball, the height is, because it's negative, is decreasing at a rate of 100 meters per second. Now notice when I put decreasing and I still keep that positive right there. Very easy to do. Okay, so I'm a Doctor Who fan. I do hope I'm not sued for this. If not, they can take it out of my the money that Nspire will pay for me for this commercial. The height of the TARDIS can be modeled by this equation. So we're going to talk about some other real world problems right here. Okay, and so the height of the TARDIS can be modeled by this equation. So again, I'm going to graph it. So I go to first thing I do, I like to clear my memory. Doc B, very quick way to clear everything. Go to Doc B. There we go, and it's gone. I'm going to graph this equation, and it's going to be, that's an equal sign, sorry. That's 200 sine of theta. We're going to use x again, x minus 23 on the outside plus 150. Now, if you know anything from pre-cal, you know that this is that midline, and this is the amplitude. So that's basically telling me in the middle of my trig function, remember sine looks like this, the middle of it is going to be 150. We're going to go with 200 above it and 200 below that. That can help us get our window. So my x max, x min, not always too worried about that. But my y minimum, I'm going to take this 150 minus the 200, minus that amplitude. Give me negative 150. I'll go negative 100 so I can see it. My y max, I take the 150 and I add 200, which is 350. But I'm going to go 400 so I can see it. And there's your graph. Now the first question says, what is the height of the TARDIS at 7 minutes? So they're asking me to find the height at 7 minutes. So to do this, using your calculator, we go to Menu. We're going to go to Trace. Don't forget, to get the value, we're at Trace. Value is the trace feature on your calculator. 5, and we want Graph Trace. And I just type in the number 7, and I get 207.581, And the unit is going to be feet. Don't forget your units on these. We're not too picky at the beginning, but later on we will be. So this says that 7 seconds or minutes, the TARDIS at 207 feet. Now again, the next question, again from pre-calc, using the calculator. Name 2 times when the height of the TARDIS is 90 feet. Now the first times that it is. So this is now saying, well, when is the height 90? We're trying to find t this time. So here's what you're going to do. On your calculator, press the tab button. It sets up f of 2. You're just going to type that into 90. You're just going to type 90 into that, and it's going to give you this little red line like so. And you're looking for where it intersects. Here and here. We don't care about these two because time is negative. Now granted, it's a TARDIS. They can go backwards in time, but we don't want those two. We want these two. Okay? So to find where time is 90, I'm just going to look at the intersection. We look at the intersection here. And to do that, you're going to go to Menu, Analyze Graph. We use this feature a lot. And is there anything here that says, intersection? Oh yeah, number 4. Intersection. Press Enter. And this is one of the coolest things we can do. Oh no, wait. It says enter the lower bound. I'm just going to press Enter here. And then it says upper bound. Now if I scroll over, if you notice, it gives me a time right there. So my first time is 1.314 minutes. And the other one, if I keep scrolling, I want the other one. If I just keep scrolling again, it's going to give me the other one right here. And I get 3.846 seconds. Minutes, sorry. So those are your 2 times. Alright. We're going to continue on with this in part 2 later. So if you want to take a look more at this, just go to part 2 and we'll take a little bit more practice on this, okay? We'll finish up the rest of this worksheet. I'll see you guys then. Bye.